So today we are going to continue solving problems on order of an element, right? So in the first class you have seen they will give one set, they will give one operation, and they will ask us to whether it's a group or not. And second class we have introduced permutation group or symmetric group, and in third and fourth class we have introduced order of an element, right? Yes. So today we are going to continue solving problems on order of an element. So there are 19 problems in the textbook. I have solved almost 14 yesterday. So today I am going to solve only 2, and then you have to do another 2 problems in your own, right? Yes. And then we will be moving on to isomorphisms of groups. So first let me quickly finish these 2 problems, and then let's move on to the fresh topic. So the 15th problem that we are going to do, actually the 14th problem I left as exercise. So page number 121. Yes, so page number 122, 15th problem we are going to do now. 15. So again the same order of an element in that topic. So 15th problem is, if in a group G, if A power phi is equal to E and AB A inverse is same as B square for all A comma B belongs to G, find order of B. Again this is also an previous year's UPSC question. So if in a group G, if A power phi is equal to E and AB A inverse is equal to phi square for all A comma B belongs to G, then we need to show that order of this B is 31. So solution. So what we need to prove? We need to prove order of B is 31. That is, we need to prove B power 31 is equal to E. This is what we need to prove, right? So order of an element means least positive integer for which A power n is equal to E. So here we need to prove order of B is 31. So therefore we need to prove B power 31 is equal to E, right? Yes. So they have given that all the elements satisfy this condition, that is A power 5 is equal to E, that is order of A is 5 and AB A inverse is same as B square. Now what I am going to do is, I am going to find AB A inverse whole square, and then I am going to find AB A inverse whole power 4, and then I am going to find AB whole power 8, and then I am going to find AB whole power 16. So I am going to find 4 things: AB A inverse whole square, AB A inverse whole power 4, AB A inverse whole power 8, and AB A inverse whole power 16. So first we will find AB A inverse whole square. So what is AB A inverse? I can write AB A inverse as AB A inverse into AB A inverse 2 times. Now I can combine A inverse into A, so which is I. So I can write this as AB. So I am not writing I here. So this is I, and this will be B A inverse, right? So A into A is I. So anything into I is again that thing. So A B. So therefore we have A B square A inverse. So we have found AB A inverse whole square. So that is AB square A inverse. Now so we have found this is equal to AB square A inverse, but you can see they already given that B square is AB A inverse, right? I am going to substitute B square now. So A into, they have given B square is AB A inverse into A inverse. Now if we make a multiplication, what we will have? So this is A into A is A square, B will be remain as it is, and this is A inverse whole square, right? So therefore AB A inverse square is A square, B A inverse square. Now we will find AB A inverse whole power 4. So AB A inverse whole power 4. So this I can write this as AB A inverse whole square into AB A inverse whole square. Right, I have splitted 4 as AB A inverse whole square and AB A inverse whole square. Okay, what I will do is you will write, I'll write this AB A inverse whole square power 2. This is same as AB A inverse whole power 4. So we have already found AB A inverse whole power 2 here, right? Let me mark this as let this 1 and let this be 2, and this is obtained, and this is by 1. So we already found AB A inverse whole square. So AB A inverse whole square is A square B A inverse square whole square, right? This value is A square B A inverse square whole square. Now I can write, I'm going to write this as two terms. So A square B A power minus 2 into A square B A power minus 2. So this I can combine these two terms again, which is equal to I. So this will be A square B A power minus 2. So which is A square B square A power minus 2. Now again we substitute B square is equal to AB A inverse. So this will be in place of B square AB A inverse into A power minus 2. So this will be, so A square into A is A cube, B A inverse into this is A power minus 3. So we have found the value of AB A inverse whole power 4. So here we have written in two terms. I have combined A inverse, I have got I, and we have, whenever you have B square, you always substitute AB A inverse. So I have found AB A inverse value is A square B A inverse square or A power minus 2, both are same. Again I am finding power 4, I am writing this as square. This value we already found. So now split this into two terms, combine these two terms. So whenever you have B square, you replace that by AB A inverse. So we have found this value. Now I am going to find AB A inverse whole power 8. AB A inverse whole power 8. So let me write here. So we need to prove. Okay, we need to prove order of B, right? So we need to prove order of B, and the answer will be 31. So in UPSC they have given like show that the order of B is 31, right? So actually the question is only find order of B. I written the answer also. Okay, so let me change the question like show that order of B is 31, right? Show that order of B is 31. It is not find, it is show that, right? Okay, so A cube B A power minus 3. So we have found the value of we have found two terms. So first term is AB A inverse whole power minus 2 is same as A square B A power minus 2. We already found this term, that is AB A inverse whole power 4 is same as A cube B A power minus 3. Now I am going to find the value of AB A inverse whole power 8 and AB A inverse whole power 16. Now AB A inverse whole power 8. So this I can write this as AB A inverse whole power 4 whole square, right? So we already found this value. So this value is A cube B A power minus 3 whole square. So this I can write this as A cube B power A into A cube B A power minus 3. I can combine these two terms, which will be I. So B into B is B square. So we have A cube B square A power minus 3. So again I am going to substitute the value of B square. So value of B square is AB A inverse into A power minus 3. So this is A power 4 B A power minus 4. Now we are going to find the value of AB A inverse whole power 16. So this I can write this as AB A inverse whole power 8 square. So AB A inverse whole power 8 is A power 4 B A power minus 4 whole square. So this is A power 4 B A power minus 4 into a power 4 b a power minus 4. So I can combine a power 4 and a power minus 4, which will be equal to I. So b into b is b square. So we have a power 4 b square a power minus 4. You again replace b square to be a b a inverse. So whenever you have b square, you have to replace that term. So this will be a power 5 b a power minus 5. Right? A power 5 b a power minus 5. Now they are given that a power 5 is e. In the question they are given that a power 5 is e and a b a inverse is equal to b square. These two they are given, right? So we have not at all used this condition so far. Now I am going to replace a power 5 is equal to e and b. So in the previous term we have only a power 4, right? Here only we are getting a power 5. So again this I can write this as a power 5 whole inverse. So this I can write this as a power 5 whole power minus 1, which is e power minus 1, which is e again. So this is equal to b, right? So we have a b a inverse whole power 16 is equal to b. A b a inverse whole power 16 is equal to b, right? A b a inverse whole power 16 is equal to b. Now we already know what is a b a inverse, right? It is b square, right? So a b a inverse b square. So this is b square whole power 16 is equal to b. So this is b power 32 is equal to b. So I can cancel 1b. So b power 31 is equal to e. Right? If I cancel 1b, so there will be 1. 1 means identity. So this means order of b is 31. So suppose in exam if they ask us to find order of b, you have to know that answer is 31. Right? Yes. So you can see here only we are getting a power 5. Right? So we have to continue and so on. Suppose in the exam if they give a power 6 means you have to continue the next term. That is you need to find a b a inverse whole power 32. Okay. So last problem we are going to do, and then we will move on to the next topic. Actually you can do any problem now. Actually this is simplifications. So 18th problem, in a group G, if xy square is equal to y cube x and yx square is equal to x cube y, then show that x is equal to y is equal to e, where e is the identity of G. The last problem that I want to do. So last problem, if in a group G, if in a group G x y square is equal to y cube x and y x square is equal to x cube y, then show that x is equal to y is equal to e, where e is the identity of G, Solution. So if in a group G these two conditions satisfies, then we need to prove that both x and y are equal to identity element. Actually it's an easy problem, I think you can do. Okay. Okay, so first we will take first condition. So xy square is equal to y cube x. So I am going to pre-multiply x. So pre-multiply x. So this will be x square y square and this will be x y cube x, right? So we have x square y square is equal to x y cube x, and we already know that y cube x, right? We already know okay. All I will do is post multiply by y square, post multiply by y inverse. So if I do that, this will be x square, this will be y power 1, and this will be xy cube x y power minus 1. So I am just substituting post multiply by y power minus 1. So y power minus 1 into y power 2 is y power 1, and here we have y power minus 1, y power minus 1. Now I am going to replace x y cube. So you can see this x cube y. Okay, so I'm going to write this as I'm going to write y cube as x y square into y x y inverse. So x y square y into y inverse. Now we know x y square. So x y square is y cube x. I am replacing that by y cube x. So let us say this is 1, let us say this is 2, and this is by 1, right? I am replacing x y square is equal to y cube x y x y inverse, y x y inverse. So we will mark this as equation number 1, right? So sorry, equation number 2. Okay, we will mark this as equation number 3. So we have x square y is equal to y cube xy inverse, right? xy inverse. Now we will take the second condition again. The second is yx square is equal to x cube by yx square is equal to x cube by. So now what I am going to do is I am going to again I can write this as yx square is equal to, I am writing x cube as x into x square y, x into x square y. Now I am writing x cube as x into x square y. We already know xy square is y cube x, right? We already know x square y is y cube x. So this will be okay. We will substitute this value, right? We will substitute x square value this. So this will be x into, so x square y is y cube x y inverse. So I am just substituting x square y, this is by 3. So I am just substituting x square y is equal to y cube xy x inverse. Okay, here we have y x square. So we have yx square is equal to x into y cube xy x inverse. Now what I am going to do is I am going to pre-multiply by y inverse. I am just going to find the value of x square. So pre-multiply by y inverse. So this will be I, y inverse into y is I. So here we have only x square, and here we have y inverse x y cube x y inverse x y inverse. So this is right? So x square is equal to y inverse x y cube x y x inverse. Okay. Now I am going to post multiply, right? Post multiply by y. Force multiplied by y. So this will be x square y, and this y will get cancelled. That means that will be equal to I. So xy cube xy x. So x square y is equal to y inverse xy cube xy x. So we will mark this as equation number 2. You can see from the first relation I have found x square y, and from the second relation also I have found x square y. So I am going to combine, this is 4. So from 3 and 4, so this is obtained by simplifying this term, and this is obtained by simplifying this term, and I am making the LHS to be x square y. So I can see here also x square y, here also x square y. So I can combine these two terms. So here it is y cube x y x y inverse, and here it is y inverse x y cube x y x. Right, y cube. Okay. Pre-multiply by y. Pre-multiply by y. So this will be y power 4. I should not cancel like this straight away. So that's why I am doing like this. So y power 4 x y x y inverse, and pre-multiply by y, this y into y inverse will be I. So we have x y cube x y x inverse, right, x y x inverse, and I am writing this as x y square into y x y inverse. I am writing y cube as y square into y, and this is same as, so we know xy square. So xy square is y cube x, right? So xy square is y cube x. So instead of this I am writing y cube x yx yx, y cube x yx yx. So we have y power 4 x y x inverse is equal to y cube x y x y x y y inverse I think I made some mistake in pre-multiply by y. So we have, this will be y power 4, and this will get cancelled. So we have x y cube yx yx this is y cube x y x inverse is equal to y inverse x y cube x y x. I think I made some mistake somewhere. Y power 4 x y okay. So here I left a y. So y power 4 x y x y inverse. Now I am going to post multiply by y. Post multiply by y. So this will be y power 4 x y x. This y will get vanished. So here we have y cube x y x y x y y x y x y. Now I can write y power 4 as y cube into y. I can write this y power 4 as y cube into y, and I can cancel left cancellation law. I can cancel y cube. So we cancel y cube. Here we have yx is equal to x yx yxy xya yxy. So I'm writing y power 4 as y cube into y, and I am cancelling y cube on both sides. I need to prove x and y are both equal to e. So, by left cancellation law, cancel y cube. So, here we have y. So, in y power 4 we have 1y, x, y, x, and this is equal to y cube will get cancelled. So, we have xy, 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 xy. So, xy, xy, xy. So, this is nothing but yx 2 times. So, we have yx whole square, and this is xy 3 times. Right. So, mark this as equation number 5. So, from the first condition we have got x square y, and from second condition we have got x square y, and we have equated two x square y's to get this relation, which is yx square is equal to xy whole cube. Now, since the given relation are symmetrical in x and y, therefore interchanging x and y, in phi we have, so if interchange, this will be xy whole square is same as yx whole cube. So why I am writing this? Because you can see the given in a given question we have xy square is equal to y cube x is the first condition. They have given two conditions, which is xy square is equal to y cube x, and second condition is nothing but the symmetry of this, changing x to y and y to x. So if I change x to y, we have yx square, and this will be x cube y. So you can see the given two conditions in the question are symmetrical. So therefore here also, since it is symmetrical, I can also change this condition. So this is xy square is same as yx whole cube, right? Yes. So we will mark this equation as 6. Now from 5 and 6, xy whole square is same as yx whole cube, and this is same as yx whole square, and this is same as okay. So we have got this, right? So from 6 we have x square is equal to yx. This I can write this as yx square into yx, and yx square we already know it is xy whole cube into yx. This is from 5. So this is xy whole cube into yx. Now here we have xy square, right? So cancelling 1xy square, so cancelling xy whole square by left cancellation law. So here we have only e, and here we have 1xy, and here we have this yx. Here we have 1xy, and here we have yx. So this is same as xy square x. This is same as xy square x. This is same as xy square x. So I need to prove x and y are both equal to e. That is my aim. Right? Yes. So we have e is equal to xy square x. So what I am going to do is I am going to pre-multiply by x inverse. So pre-multiply x inverse and post multiply by x inverse. So this will be x inverse x y square post multiply by x inverse, right? So that is, this is obtained by pre and post multiply x inverse, pre and post multiply x inverse. So this is nothing but x power minus 2 and this is nothing but y square, because this is x, this is x, this is I, this is I. So we have x power minus 2 is equal to y power 2, right? X power minus 2 is equal to y power 2. So mark this as equation number 7. Okay. Now, so what is the condition they are given? Now they are given two conditions, right? The first condition is x y square is equal to y cube x. So this is the one we wanted, right? So for this condition only we have worked so hard, right? So for the first condition they have given x y square is equal to y cube x, right? X y square is equal to y cube x. So instead of y square I am going to put x power minus 2. Instead of y square I am going to put x power minus 2 and I can write y cube as y square into yx, and instead of y square I am going to write as x power minus 2. So we have x into x power minus 2 is equal to x power minus 2 yx, x power minus 2 yx. Now x into x power minus 2 is x inverse, x into x, this x inverse, and x power minus 2 into x. Okay, we will write this as y into y square x. So y into y square is x power minus 2x. This is y x inverse, right? Y x inverse. So this means if we post multiply by x inverse whole inverse, so we will get y is equal to e. This is the first thing we need to prove, right? And with the help of second condition we will prove x is equal to e, right? So we have worked very hard for obtaining this condition, which is x power minus 2 is same as y power 2. So from the first condition we have got y is equal to e. Now what is second condition they have given? The second condition they have given is yx square is equal to x cube by. So we know y square is x power minus 2, right? We know y is x power minus 2. So we need to transform everything in terms of x. So what we will do is we will write y in terms of x, right? Y in terms of x. So this will be y x square is equal to x cube by x power minus 2 is equal to okay, here we have y is equal to e, right? So I can substitute this here, this 8. So I can substitute e into x square is equal to x cube into e. So we have x square is equal to x cube. This means x is equal to e. So this is from 8. So therefore x is equal to y is equal to e, right? That's it. So this can be asked in long question. So we need to prove that if xy square is equal to y cube x and yx square is equal to x square y, we need to show that both are equal to identity element. So we have worked hard to find that x power minus 2 is same as y power 2, and if you got this result, you just memorize this result, and if you got this result, you can just substitute in two conditions to get x is equal to e and y is equal to e. Now again 19th you can do, right? Last problem is 19th problem. So I will only explain what that statement tell, right? What that statement tells. So I only explain the statement. The proof is just only 4 to 5 lines. I think you can easily follow the proof. So I only explain the statement and then we'll move on to isomorphisms of groups. So let G be a group. So let G be a group and let A belongs to G, and let A belongs to G, be a finite order n, be a finite order n, that element is of finite order n. Then for any integer k, then for any integer k, order of a power k is equal to n by GCD of n comma k. This is what this theorem says. So again you consider the known group. Let us consider the group G is equal to 1 minus 1 I minus y, right? So we know that order of I is 4. Order of I is 4. Suppose in the exam, find order of I power 1000. Suppose you need to prove what will be my order of I power 1000, right? First you need to find I power 1000. I power 1000 will be one of the element 1 minus y I minus y, because the closure property, if you multiply any times it will be in the group G. So I power 1000 will be 1 minus 1 I or minus I. So it will take long time, right? So with the help of this result, what we can do is, so just compare here. So order of a power k is equal to n by GCD of n comma k. So you can see n is the order of I, right? N is the order of element we are choosing and k is the power we are raising. So if we compare here, n is equal to 4, k is equal to 1000, because order of I is 4 and k is 1000. So what will be my order of I power 1000? So n is 4 by GCD of n is 4 and k is 1000. So what is the GCD of 4 and 1000? It is 4, I think, right? The greatest common divisor for 4 and 1000, it is 4. So 4 by 4, so which is equal to 1. So you can quickly straight away do this in fraction of second. If you know the formula, order of a power k is equal to n by GCD of n comma k, where n is the order of a and k is the power we are raising. This is what the 19th exercise is saying. So you can do this very easily, right? 3 to 4 lines proof, you can follow that. So we are moving on to the next topic, which is if I have left 2 or 3 problems, you have to work out. I can't do all the problems. So we will move on to the next topic, which is isomorphisms of groups. Very important topic in concept point of view as well as in exam point of view. Before that, I will fill off inks. இருக்கு Okay, we will start isomorphisms of groups, right? So we have completed 3 topics. Isomorphisms of group, right? So what this means is, so suppose if we have a 2 group, let us say it is G, and let us say we have another group G dash, right? So even though it may look different, the structure may be different, right? So but if the properties are same, structure may be different, but if the properties are same, then we say the 2 groups are isomorphic. Right? Like for example, if I have a phone, right? Let us say it is a phone. Let us say we have another phone, right? So let us say these 2 phones share a same specifications, right? Same specifications. So for example, if it has let us say 64 megapixel camera, again this phone also has 64 megapixel camera. So suppose if it has 6 GB RAM, this also has 6 GB RAM. But this brand is different, this model is different, right? So this is white color, this is black color, and it is some oval in shape, and this is some rectangle in shape. So you may see, even though the structures are different, but they share the same property. Property means what this do can also this do. What this does, same this does also. So we say these two are isomorphic. Even though the structures are different, but the properties they are showing are same. So let me try to relate this example with this group. So even though the structures are same, so if it is abelian, this is also be abelian. If this group is cyclic, this group is also cyclic. If this group has an element of order 2, then this also has an element of order 2. If this group has 4 subgroup, then this also has 4 subgroups. So even though structures may be different, we say both are isomorphic when if they satisfy 3 conditions. That's what I'm going to define first, right? So not all 2 groups are isomorphic. So if they share some condition, then we say both are isomorphic. So what are the conditions? So first we will define when 2 groups are isomorphic. So first let us define that, and then we will work out some examples. So definition, isomorphic mapping. Definition. Isomorphism. Let G and G dash be 2 groups. Let G and G dash be 2 groups. Right? Let G and G dash be 2 groups. The composition is simply a mapping F. So a mapping F from G to G dash. I am going to define a map from G to G dash. If this map satisfies some condition, then we say that map is an isomorphism. A mapping F from G to G dash is said to be isomorphism if the following conditions are satisfied. The first is F is 1 to 1. That map has to be 1 to 1. That is, distinct elements in G have distinct images. And the second condition is F of AB is equal to F of A into F of B. Right? Yes. Now we will call this, actually in this book they are following a different way. If you look at the standard textbook, first they will define homomorphisms, and then they will extend homomorphism to isomorphism. But they are following reverse in this book. The first they are defining isomorphism, and then they are defining homomorphisms. So this condition is called homomorphism. So 2 groups are homomorphic if F of AB is equal to F of A into F of B, and they are isomorphic along if this satisfies 1 to 1, right? So this condition is called, actually this we will define later, so just understand this homomorphism. So f is a function from g to g dash, then the map is called homomorphism if f of a b is equal to f of a into f of b. It is called isomorphism if it is homomorphism and it is 1 to 1. If it is homomorphism along with 1 to 1 will be isomorphism, right? F of a b is equal to f of a into f of b, and you can see a b is the operation that we are defining in g. This operation is defined in g dash, right? Yes. That is image of product is same as product of images. So if there exists a map, then we say that both are isomorphic, right? So if we can find a function from g to g dash that satisfies these two conditions, then we say both two groups are isomorphic. We will write g is isomorphic to g dash. So if we can find a mapping f that is homomorphism and 1 to 1, then we say that map is that then two groups are isomorphic. So you can see note 1 in our definition of isomorphism of two groups g and g dash, we denoted the compositions in g and g dash both multiplicatively. The student can use different symbols to denote the compositions in g and g dash, but there should be no confusion. So what they are saying is, so let us define this to be star, right? So this star is the operation that we are choosing in g dash. Note 2, if g is isomorphic to g dash, then there exists more than one isomorphisms of g onto g dash. There may be many 1 onto functions from g to g dash, but if there exists at least one function f which is 1 onto and also preserves composition, then g will be isomorphic to g. So what they are saying is, there can be many 1-to-1 mapping from g to g dash, but if you found only one, then it is enough for us to say both are isomorphic, right? So there can be many. I will repeat, if g is isomorphic to g dash, there may exist more than one isomorphism of g onto g dash. There may be many 1 onto functions from g to g dash, but if there exists at least one function which is 1 onto and preserves compositions, then g will be isomorphic to g dash. So let us add one more condition also. Let us add the third condition is f is onto. This will also be important, right? So 1 onto and f of a b is equal to f of a into f of b, then we say both are isomorphic. So isomorphic means 1 to has to include. So note 3 is, if a group G is finite, then G can be isomorphic to G dash only G dash is also finite. That is, if this group is finite, this should also be finite. We cannot say one finite group and infinite group are isomorphic, right? So at the beginning itself I said the structure should be, even though the structure is different, but the properties should be same. But by looking itself, if one is finite, one is infinite, how can both be same, right? So if a group G is finite, so if this is finite, then G can be isomorphic to G dash. It can be isomorphic when G dash is also finite, right? So we can only say, we can talk about isomorphism, whether this F exists or not, that doesn't matter. But if this is finite, this has to be finite, then only we can able to find such one to, right? Because if this is finite, this is infinite, how can onto exist? Onto does not exist, right? So this is finite, this is infinite. So this is cardinality of this set is same, cardinality of this is finite, cardinality of this set is infinite. That means we can only map some elements to here. So we will have some empty set empty in G dash, that will be onto fails. So if group G is finite, then G can be isomorphic to G dash only if G dash is also finite. and the number of elements in G is equal to number of elements in G dash, and also if both are finite also number of elements should be same. Suppose if this group has 4 elements, then we can define isomorphism to some other group. It must also have 4 elements, same cardinality should be same, otherwise there will be no mapping F from G to G dash which is 1 1 as well as on 2. So what they are saying is we cannot make isomorphism between a finite group and an infinite group, and also if two groups are finite also the cardinality should be same, then only we can define isomorphism between two groups. Note 4, if the group G is isomorphic to group G dash, then we say that group G and G dash are abstractly identical. Even though structure may be different, but algebraically they are same. Algebraically they are same means they have same properties. So we will call that as abstractly identical. From the point of view of abstract algebra, we shall regard them as one group and not as two different groups. Very important. In the context of abstract algebra, we shall regard them as one group and not as two different groups. So if you say this group has 4 elements, let us say define some other group that is also 4 elements. If there exists a mapping F from if there exists isomorphism between the both two groups, you should regard both as same group. You should not consider them as two different groups. Both are same groups, even though structure may be different, the properties are same. So when you count, you should take only as one group, right? So this is the introduction to isomorphisms of groups. So first we will see some examples. So example 1, example 2, example 3, example 4, some important properties. Okay, we will have 4 examples now, right? So we have 4 examples. So let us relation between isomorphism. Okay, this is only small topic. So we will see some examples. So example 1. Example 1. If R is additive group of real numbers R plus the multiplicative group of positive real numbers, prove that the mapping F from R to R plus isomorphism. R is the additive group of real numbers. So I'm going to define I'm going to say R plus. So G is equal to R plus. G is equal to R plus. Okay, let us define R. Let us take G to be equal to R comma plus. We know this is a group, right? A set of all real numbers under addition, under binary option R. I'm going to define G dash. So this is example 1. Example 1, that is positive real number under multiplication. Positive real number under multiplication. So I'm going to say both are same, right? So it will be more interesting, right? So set of all real numbers under addition is isomorphic to the set of all positive real numbers under multiplication. So if I say both are isomorphic means I need to create a map that is 1 1 onto 1. F of AB is equal to F of A into F of B. Right? So I'm going to define a map F from R comma plus to R plus comma dot, right? So this is real number with respect to addition and a positive real numbers with respect to multiplication. The map is F of x is equal to e power x. F of x equal to e power x. So you can see e power x is defined only for what is the range of e power x? E power x range is positive real number only. So that's why we are defining positive real number here. And if you take any number, this x belongs to G, and the output will be in G dash, right? So this is the map I am defining. So first I am going to show that F is 1 1, F is on 2, and I am going to show F preserves composition. That means f of AB is equal to f of A into f of B. So first f is 1 1. So you know how to prove 1 1, right? So f of A is equal to f of B implies A is equal to B. This is the one we will prove for 1 to 1. So let us take suppose f of e power x is same as f of e power y. F of e power x is same as e power y, then I need to prove x is equal to y. So okay, so f of x1 is equal to f of x2, suppose. Then I need to prove x1 is equal to x2, right? So f of a is equal to f of b plus a is equal to b. So that is, you collect two elements a and b in the domain, and if f of a is equal to f of b, then I need to a is equal to b. This is the condition for 1 1. So I am collecting two distinct elements. Let us say two elements, let x1 comma x2 belongs to G. So let x1 comma x2 belongs to G, and suppose if f of x1 is equal to f of x2, f of x1 is equal to f of x2. What is, I need to prove x1 is equal to x2. So what is f of x1? E power x1. This is e power x2. So I can always equate the power, right? So if base are same, I can equate the power. So this implies x1 is equal to x2. So this implies f is 1 1. F is 1 1. Now I need to prove second condition is f is onto. F is onto. So for onto, for every element in the codomain, there exists pre-image. If I say that will be onto, right? For every y in G dash, for every element in the codomain, there has to exist a pre-image. For y, there has to be pre-image. Then only it will be onto. Then only codomain will be equal to range. For every y belongs to G dash, there exists for every y belongs to G dash, we should prove there exists, we should prove there exists some x such that f of x is equal to y, right? So that is this y as pre-image. For every y belongs to G, we should prove that there exists x such that f of x is equal to y. That is, for every y we need to prove there exists. So let what is f of x? This is e power x, right? That is, e power x is equal to y. So if I take log on both sides, so there will be log x, it will be x is equal to log y, right? So there exists x, for every y there exists x such that x is equal to log y. So therefore it is for every element in codomain there is log y, right? Yes. And again you can see this y is log x is defined only for positive numbers, and see y, where is y? Y is in codomain, and what is the codomain? It is R plus. So therefore this is defined. Suppose if you say this is it is not only R, if you say it is R star, a set of all real numbers, this map will not be onto, right? Because you can see log y is defined only for y is positive number, but since this is y is in this also include negative numbers, this will not be defined, but we are defining only R plus, set of all positive real numbers under multiplication. So this is defined. So therefore this is onto. Now I need to prove this preserves third condition, that is f of AB, f of xy is equal to f of x into f of y, right? So what is f of xy? It is e power xy. So I can write e power xy as e power x into e power y. So e power x is f of x, e power y is f of y. So it preserves, f preserves composition, f preserves composition. So I have found a map f that is 1 1 onto 1 homomorphism. So therefore G and G dash are isomorphic. This is the first example. So move on to second example. Let R plus be the multiplicative group of all positive real numbers. So second example. So suppose in the exam, if they say define isomorphism and give two examples, means you have to give this example and you have to prove that it is isomorphism. Second is G example 2. R plus B the multiplicative group of, so I am taking R plus comma dot. So the set of all positive real numbers under multiplication. Remember 0 is not positive, right? G dash is equal to the set of all, and this change, you can see both are I'm just in the previous problem we have defined a map from this to this. Now actually this problem, actually we don't need this example, right? So whenever when I in the previous column I have said there exists a map F from G to G dash, that means automatically this is also isomorphic, right? So that the inverse mapping will be isomorphism. So what is the inverse for log x? Sorry, e power x, it is log y, right? So therefore the map F from G to G dash defined by f of x is equal to log x is a isomorphism, right? So from this what you can conclude is, if I say there exists a map F from G to G dash which is isomorphism, then automatically there exists a map from G dash to G, that mapping is the inverse mapping of F. So automatically if this is isomorphic to G, then if this is isomorphic to G, then surely this is also isomorphic to G, right? So that is the one they are trying to say, right? So if I define the map f of x equal to log x, so automatically this is also an isomorphism. So we need to prove this is 1 1. So f is 1 1. So f of x1 is equal to f of x2, that is log x1 is equal to log x2. So this implies x1 is equal to x2, and again f is onto, right? So for every y in codomain there exists x in domain, there exists x in domain such that this y is equal to e power x, right? Y is equal to e power x, and it is also homomorphism, that is it preserves composition, that is I need to prove f of xy is equal to f of x into f of y, and so what is f of xy? It is log xy, and we know log AB is log A into log B. So this is f of x, this is f of y. So therefore it satisfies three conditions, right? Yes. So third example, show that the additive group of integers isomorphic to okay, these are very basic example. So we'll move on to the fourth example, right? Third example you can refer that, right? The same example. Show the set of all complex numbers under addition is isomorphic to identity mapping as well as under the mapping which takes very complex numbers to conjugate of complex numbers. So example 3. So G is set of all complex numbers under addition, set of all complex numbers under addition is isomorphic to itself, it's isomorphic to itself under the identity mapping as well as under the mapping which takes G dash, that is I am taking two same group, right? Same group. So we are trying to define automorphism, that we will define later, and isomorphism from G onto itself is called automorphism, right? So we will define that later. Actually that is not in our syllabus. So if there exists an isomorphism from the group onto itself, then we say that is automorphism. Just remember the word, but it's not in the syllabus. Okay, C comma plus to C comma plus again. The map is identity mapping. Map is there are two isomorphism. So first is G to G dash defined by f of z is equal to z. This also defines an isomorphism from this to this. And second map f from G to G dash, that is f of z is equal to z bar. So there are two mappings, that is one onto one homomorphism, that is f of ab is equal to f of a into f of b. So there exists two mapping such that let us say this is f, let us say this is g, right. So I think this is like, I think you can prove this very easily, right. So you can see this identity mapping. Identity mapping is always 1 onto, and you can see it will also split, right. That is f of z1 is equal, and very important, f of z1 plus z2. Here you have to write, you have to prove f of z1 plus z2. In the previous problem we have proved f of z1 is equal to f of z1 into f of z2. Why? Because the mapping f from G to G dash, and this G dash is this group is under multiplication. This group is under multiplication, and this group is under addition, right. So that's why we have multiplication here. That's why we have multiplication here. So here here we will have f of z1 plus z2 is equal to f of z1 plus z2. You can see here operation is addition, and here operation also addition. So therefore our output will be f of z1 plus f of z2, right. So again you can see this map is 1 onto, and clearly this will satisfy, and f of z bar okay, right. Again you can also seek this also. So f of z1 plus z2 whole bar is same as f of z1 bar plus f of z2 bar. This is my conjugate property, and this will be homomorphisms also. So these are some examples for isomorphism. So now we will prove some property based on isomorphism. So there are three important properties, so that we will prove that. So we have three properties, and then we have two exercise problems. Okay, I think I have finished almost, right. So we have three properties and two exercise problems and some 2 to 3 problems. Actually overall we have only 7 to 8 problems that we are going to do overall. So properties of, so suppose in exam if they say state and prove all the properties of isomorphism, means you need to prove three properties. So properties of isomorphism. Let F be an isomorphic mapping of a group G onto G dash. So let F be an isomorphic mapping. Let F be an isomorphic mapping from G onto G dash. G onto G dash. Then we have the following properties. then we have the following property. The first property is, so already they are given that this is an isomorphism. Let F be an isomorphic mapping from G onto G dash. That means F is 1 1, F is onto, and F of A B is equal to F of A into F of B. So these are the conditions that we are assuming in the beginning itself. The first, the F image of the identity, the F image of the identity E of G is the identity of G dash. It's a natural identity of G dash. That is, F of E is the identity of G dash. So if you have G, so if you have G dash and this E is the ID of G, then this is a isomorphism. Then E will have some image F of E, and this F of E is the identity for G dash. This is the one first we need to prove. That is, the image of E is the identity for G dash. So G dash will have identity because it is also a group, right? So that ID will be F of E. So if this is an isomorphism, then if E is the ID of G, then F of E will be the identity of G dash, right? So that is F of E. If E is the ID, E is the ID of G, then F of E is the identity of G dash. That is what the first property. So proof, right? Yes. Now already they have given that F is an isomorphic mapping. So from this we can say F is 1 1, F is onto, and F of AB is equal to F of A into F of B. So these three conditions already we are in assumptions. Now we will prove, we have to prove that F of E is the identity of G dash. So let E be the identity of G. So let E dash be the identity of G dash. So what we need to prove? F of E is equal to E dash. That is what we need to prove, right? So that is to prove F of E is equal to E dash, because E dash is the identity of G dash, right? F of E is equal to E dash. This is the one you need to prove, right? Yes. Okay. So we will prove this. So let A belongs to G. Let A belongs to G. Then what can you say about F of A? This will be in G dash. This will be in G dash. Why? Every element will have some image. Then only it will be a function. Right? Then only it will be a function. Therefore, the image will be in G dash. So this implies F of A. Suppose if doesn't happen, then this is not at all a function. If it is not at all a function, then we cannot talk about 1 1 and onto. But this is already 1 1 and onto. Therefore, first it has to be a function. So therefore, F of A belongs to G dash. Okay. Now E dash into F of A, that is F of E into E dash, right? That is, now we are finding E dash into F of A. So what is E dash? E dash is the identity of G dash. So E dash into F of E, right? So I can write A as E into A, right? I can write A as E into A. That will not change, right? E into A. So we already know F is isomorphism, so I can write this as F of E into F of A, right? Why? Because F is iso, right? F is iso means that is F of AB is equal to F of A into F of B. So here we have E dash into F of A. So by right cancellation law, what we can do? By left cancellation law, this E dash and this E dash we can cancel, and by right cancellation law, this F of A and this F of A we can cancel. So we have left with E is equal to F of E. So what is F of E? E is equal to F of E. What is E? E is the ID element of E dash into Yes, wait. Now E dash into f of a, right? E dash into f of a. So this is same as, what is E dash? It is the ID element of G dash, right? E dash is the ID element of G dash. And what can you say about E dash into f of a? This is equal to f of a, because ID element into something is same, and you can see this E dash is somewhere around here and f of a is somewhere around here, and this is, since this is ID element, so I into f of a is same as f of a, right? You have to be very careful. This E dash is here and this E dash is the ID element, so I into f of a, you should treat this as I into f of a, both are in same set for this f of a. So I can write f of a as f of e into a. So I can write f of e as f of e into f of a. So here we have e dash f of a. So by right cancellation law, this implies I can cancel this f of a and f of a. This is e is equal to f of e dash. We have proved, right? E is equal to f of e dash. So therefore, what is f of e? E dash. What is e dash? E dash is the ID element of G dash. So therefore, f of e is the ID element of G dash. Since E dash is the ID element of G dash, and since G dash is same as f of e is the ID element of G dash. This is the first property under isomorphism. The first property is, if E is the ID element of G, then f of e will be the ID element of G dash. This is the first property, right? So first we have started, actually it's a 2 to 3 line proof. So this is the one we need to prove, right? And you just remember this condition. After this, I can write a as f of e into f of a, and since it's isomorphism, I can split f of e into f of a, and by right cancellation law, I have proved. So this is the first property we have proved. So we'll move on to second property. Now, second property is the F image. The F image of the inverse of an element A in G is the inverse of the F image of A. That is, f of A inverse is same as f of A whole inverse. So first we have said that if E belongs to G, then f of E will be the ID element of G dash. Here what we are saying is, you just take, so here we have G, here we have G dash, and this f is isomorphism. That is, f is 1 onto 1, f of A B is equal to f of A into f of B, and you just, if you find A inverse, right, A inverse, then this here will be f of A inverse, right, f of A inverse, and this is same as f of A whole inverse, right? That is, it preserves inverse also, right, it preserves inverse also. So we need to prove f of A inverse is same as f of A inverse. The f image of an inverse of an element, the f image of an inverse of an element is the inverse of f image of A, is the inverse of f image of A. Proof. Let E is the identity of G. E dash is the identity of G dash. E is the ID of G and E dash is the identity of G dash. I need to prove f of A inverse is equal to f of A whole inverse, right? Yes. Now let A belongs to G. Let A belongs to G. Now what can you say about A inverse? It will also be in G. F of A will be in G dash. But what can you say about A inverse? So A inverse also in G. A inverse is also in G. And what can you say about A into A inverse? It will be equal to E. It will be equal to E. Now I need to prove F of A inverse is equal to F of A whole inverse. Now we know that E dash is equal to F of E. That is the ID element of E dash is same as F of E. This is by first property, by property 1, by P1. By property 1, we know that E dash is the ID element of G dash and E dash is same as F of E. Now I can write F of E as F of A into A inverse, right? So since F is an isomorphism, I can write F of A into F of A inverse. It is given that F is, let F be an isomorphism, then only I can write, right? So we have what is E? So we have E dash is equal to F of A into F of A inverse. E dash is the ID element of G dash. So all these elements are in G dash. So this element into something gives me ID element. That means the inverse of this is this. That is, the inverse of F of A is F of A inverse. This is the one we need to prove, right? Inverse of F of A is F of A inverse. This is the second property. So this is a normal, right? Something into something gives you E means the inverse of X is this element. So here we have inverse of F of A is F of A inverse. So we'll move on to third property. The first property is it preserves ID element and also it preserves inverse. So third property. The third property is then the beginning I have said the order of an element A belongs to G is equal to order of its image. Very important. The order of an element A of G is equal to order of its image. Order of its image F of A. That is order of A is same as order of F of A. If remember, these all will be true, all property will be true if that map is isomorphism, then only this all this be true. At the beginning itself, let F be an isomorphic mapping from G on to G dash. Okay, so proof. So order of A is, we need to show that it is order of F of A. So let E is the identity of G. F of E is the identity of ID of G dash, right? F of E is the ID of G dash. Now let the order of A be finite and it be equal to n. Let order of A be finite and be equal to n, that is order of A is equal to n. I am assuming that it is finite and it is equal to n. So order of A is equal to n means A power n is equal to E. This is my definition, right? Order of n means A power n is equal to E. Now A power n is equal to E. So taking F on both sides, so F of A power n is same as F of E, right? F of A power n is same as F of E. Now what I can write A power n as F of A into A into A into A n times, right? N times is equal to F of E. So F of A into A into E. And this is an isomorphism. And remember, if it is isomorphism means it is not only true for two element, right? It is true for n element. F of A, B, C, D is same as F of A, F of B. I can bring F inside, right? And again you can see this is an isomorphism. So what I can do? I can bring f inside. So this is f of a, f of a, f of a, f of a n times is equal to f of e. So we have f of a n times, f of a n times, that is f of a whole power n is equal to e. This is true or not? We have f of a n time, f of a n time, we can write this as f of a whole power is equal to e, sorry, f of e. Right. So what can you say about from this? F of e is the ideal element of g dash, and what can I say about order of f of a? It is also equal to n. Order of f of a is equal to n, because you can see f of e is the, so you have to treat all the elements in g dash. Alright. So this is f of a and this is e. So f of a for something gives me ideal element, that means order of f of a is n. Therefore, we have started with order of a is equal to n, and we have proved that order of f of a is also equal to n. Okay. What we need to prove is we cannot say about it is not equal to n, it will be less than or equal to n, right? Because n is the we assume that it is equal to n, and we cannot say it is equal to n. If it is the least, it will be equal to n. But less for the safer side, we will assume that order of f of a is less than or equal to n. Suppose if this n is the least positive integer, it will be equal to n. That is what I have stressed in the previous videos. So let us mark this as equation number 1. So we have order of f of a is always less than or equal to n. So now we will move on. We will show that this is greater than or equal to n, and we will prove that both are equal. So from the first case, that is by first equation, we have order of f of a is less than or equal to n. Right. Now consider. So let order of f of a is equal to m. Let us assume that order of f of a is equal to m. Order of f of a is equal to m. From this, what I can conclude? F of a whole power m is equal to e. F of a whole power m is equal to e. And f of a m times, right? So f of a up to f of a m times is equal to e. So this means this I can write this as, I am just making a reverse process. So f of a m times is equal to e. So this I can write this as f of a power m is equal to e, and this I can write this as f of a power m is equal to e, and this f of e, right? Sorry, because order of this is equal to m means f of e is the ideal element of this. This is f of e. So this means order of a power m is equal to f of e means order of a power m is always less than or equal. Order of a power m is equal to f of e means order of a is always less than or equal to m, right? So first, second, third, fourth, fifth, sixth. So from this we have to come here. So we have order of a is less than or equal to m. So what I have assumed, order of a is n. So n is less than or equal to m. So from 1 we have order of f of a is less than n. So we have assumed order of f is equal to m. So we have m is less than or equal to 1. So this is by 1. Right. So from 1 and 2, n is equal to m. So therefore order of a is same as order of f of a. Order of a is same as order of f of a. So these are the 3 important properties about isomorphisms. Right. So important note, suppose we are able to prove that a group G is isomorphic to another group G dash, then we should try to find a 1-1 mapping from G onto G dash, which also preserves composition in G and G dash. While forming such a mapping, we should keep in mind the above three facts that an isomorphic mapping must preserve identity, inverse and order. So, suppose in exam, if they ask, show that isomorphic mapping preserves identities, inverse and orders, you need to prove these three conditions, right? Yes. That's what they are saying. Important note, suppose we are to prove that a group G is isomorphic to another group G dash, then we should try to find 1 mapping from G onto G dash, right, which also preserves compositions. That is, we need to find 1 mapping and f of a b is equal to f of a into f of b. That is what they will say preserves composition, means f of a into f of a b is equal to f of a into f of b. While forming such a mapping, we should keep in mind the above three facts that an isomorphic mapping must preserve identities, inverse and orders, right? Yes. So, there are two examples. There are two examples. The first example is, show that the multiplicative group 1 minus y I minus y is isomorphic to permutation group, right. So, this is the first example, that is, we need to prove that the fourth root of unity is isomorphic to the permutation group I, A, B, C, D, A, C, B, D, A, D, C, B. They have given 4 permutations, that is, they have taken 4 elements from S4. In S4, they have taken, in S, we have 24 elements, so they have collected only 4 elements, which is I, A, B, C, D, A, C, B, D and A, D, C, B. We need to show that both are isomorphic. Very, very important problem in exam point of view. And second problem is, show that the multiplicative group, that is a 1 omega square, that is a cube root of unity is isomorphic to a subgroup of S3, right. This is the second problem. And third is, the map, the 0, 1, 2, 3, that is addition modulo 4 is isomorphic to multiplication modulo 4. So, these are the 3 exercise problems that we have in isomorphisms. And then there is some relation, that is isomorphism is the equivalence relation, that one we need to prove. And then there is one theorem, that is transference of group structures, and then we are done with isomorphisms of groups, right. And then we will move on to a concept of subgroups, and then we move on to concept of subgroups. So, the first problem is, show that the multiplicative group G 1 minus 1 I minus I is isomorphic to a permutation group. It's a very important concept. Later we will study Cayley's theorem. In Cayley's theorem, we will say that every group is isomorphic to a subgroup of permutation group. Whatever group you take, every group is isomorphic to a every group is isomorphic to a subgroup of permutation group. It's a very important theorem that you will come across later, which is called Cayley's theorem. So, we will do these 3 problems. I think only one is watching. If you are interested, I will continue, or else you will see in the next class. I don't know who is one watching. Can we continue or not? Yes or no? Quick. Next class. Okay. As with tomorrow, there will be 50% chance that there is a class. So I thought that I will finish, that I will go for another 1 hour. Okay, I'll find you tomorrow, right? So, we need to prove 3 exercise problems That is, we need to show that the fourth root of unity is isomorphic to a subgroup of S4 and third root of unity is isomorphic to a subgroup of S3, and one more problem, and then we need to prove that isomorphism is an equivalence relation. That is, isomorphism is an equivalence relation we need to prove, and then there is one theorem, that is a transference of group structure. So far only we have 5 problems we have left, right? So that we will do tomorrow, and then we will wind off isomorphisms of groups, and then we will go on to subgroups and normal subgroup, quotient groups, etc. Right? Yes. So if you have any doubt, you can ask, or else I will wind off. No doubt, right? Okay, thank you.